Hey, welcome to the logarithm introduction. We are going to today discuss what are logarithms. How are they really made up of? I know we've talked about how they graph, but we're really going to get into what they are and how they connect to exponential. So let's go ahead and discuss this first problem. So if I have 5 to the x is equal to 25, that's the same as me saying 5 to the x is equal to 5 squared. That didn't change anything. All I did is change 25 into another way of writing it. And these exponents, we have the same base, and therefore the exponents must match in order for this to be true. So we can easily figure out what I need to raise 5 to equal 25, because it's a number, it's a basic number. In other words, it's a integer value number. But what we run into is sometimes they're not. So let's look at another problem. If I said I have 6 raised to some power is equal to 27, how can I find that power? I can't go 6 to something is equal to 6 to the x, because what do I need to raise 6 to get to 27? 6 squared is 36. And so I know the numbers between 1 and 2 for the exponent, but what decimal between the two am I going to find? I could sit there and plug in all the decimals and I would eventually maybe find it. But logarithms help us get to the exponent spot. So let's go ahead and go back to this, and I'm going to show you how this can be rewritten as a logarithm. So the 6 is the base of the exponent. The x is the exponent. And I call this 27 the answer. And so one of the things that we'll be needing to do today to help us solve the problems today when we're just simply evaluating logarithms in the first step is you're going to have to convert this over to a logarithm, or convert from a logarithm over to an exponential. And so let's talk about how you convert. So to rewrite it, there are several spots. You're going to have log base something of a number equals another number. So you have 3 number spots. They follow a pattern when you convert. So when you convert, you start off at the base. The base number is going to be the same on both sides. And so you have a base on both sides. That base number, in this case, is a 6. So I'm going to write this number as 6. The next number you're going to get to is going to be the answer. And so the next spot, I'm going to change this, and I'm going to write 27 is equal to the last spot, the x. And so you take your base of your exponential and your logarithm are going to match. So the base is the base. The other 2 numbers just switch locations. I call it, the visual I do it over here is with the orange is a fish. Sometimes I make it look more like a fish than others, but that's what I always call it. So if I ask you to fish something, that's what I'm asking you to do, is convert it, switching around the places. But really all it's doing is switching these 2 locations. It's switching the answer and the exponent, so which side they were on. It's making our exponent our answer. Later on in this unit, we are going to learn how to evaluate the log base 6 of 27 and find out the decimal number it is. But for today, we're just going to be working on switching them back and forth and then evaluating from the exponential. Okay, sometimes you'll have a log of some number, let's say 25, but you'll see that there is no base written. That base is understood to be 10. When you see ln of 25, this is meaning log base e of 25. So these are the log base 10, the one that was without something written, is called the common log. And this is the natural logarithm. So common, if there is no base written, it is understood to be a base 10 because we count in base 10. We count every 10 numbers, repeat the cycle. So our numbering system is already set up for base 10. So that is the reason this is the common log. And the natural log is going with the natural exponential function. So let's evaluate these two problems. I'm going to do number 3. Y'all are going to do number 4. So let's do log base 4 of 16. Step 1 is I am going to put it equal to x. That way I have an equation set up. Step 2 is me converting this into exponential. So when I convert this to exponential, it's going to be 4 to the x equals 16. And like I said, it's just basically these two switch spots and you fill into the format. So it's going to be a number raised to a power equals a number if you're converting into exponential. And so now I need to think about 16. 16, is it 4 times what equals 16? Well, 4 times 4. So 4 squared is equal to 4 to the x. We now have the same base. Those exponents would match. And so we have x is equal to 2. Y'all are going to do number 4 on your own and check the answer on the side. So let's look at this next one. So what is different this time is if you notice our base is our larger number. So on this one, our bases were smaller than our answer portion. So let's look at what happens whenever the base is the smaller value, or is the larger value. So first off, let's go ahead and convert this over into a logarithm, or over into exponential. So again, our base is 8. So we have 8 to some power is equal to 2. Some of you may be able to recognize the power right away, and those that can, that's fine. You can go quickly to it. If you do not recognize the power right away, let's find out if we can have it to where they have the same base. And so we need to find the smaller of the two bases. So this is 2 to the first. So can we get 8 into 2 to some power? So 2 squared is 4. 2 cubed is 8. So I am going to convert 8 into 2 cubed. So this is 2 cubed to the x power. And so remembering our product power of exponents, it just makes that a 3x. Is equal to 2 to the first. And so knowing our properties of exponents, that means these two exponents must be equal. So 3x must equal 1. So if I'm solving for x, x is equal to 1/3. And so we can check this by saying, is the cube root of 8 equal to 2? And the answer is yes. Because remember, when we have that fractional power, we're making 8 to the 1/3, that is the same thing as the cube root. I want y'all to go ahead and do number 6 on your own. So if you'll notice on these, we have the same situation. We have the base being the larger number, but you'll notice that our other number is not prime. And so we need to take time and see what we need to do when we convert this. So step 1 is set it equal to x. And so I can convert to my exponential. So 243 to some power is equal to 9. What I usually do is I start with a smaller number, so 9. What is 9 made up of? Well, 9 is 3 squared. Now let's see if I can convert the 243. And so I'm going to take 243. I already have an idea of what my base is going to end up needing to be if this is going to work. It needs to be 3. So if it's not 3, then this is not the way I'm going to be able to solve this. So I'm going to take and divide it by 3. And 243 divided by 3 is 81. 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. So that means 3 to the 1, 2, 3, 4, 5 is 243. So 3 to the 5th, and then we bring that x in. So now our bases match, so that means that our exponents should be equal. And so when I set those exponents equal to each other, I have 5x is equal to 2. Divide both sides by 5, and I end up with 2/5. And so our answer is 2/5. I can check that by taking the 2/5, so 243 to the 2/5 power, and you can double check it. I want you to do number 8 on your own. Okay, the last scenario we'll end up with is when you have something with a 1 in the numerator. This is an automatic clue that the answer is going to be negative. So if you ever see that, your answer is going to be negative. And so now let's figure out what it is. And so step 1, set it equal to x. And we're going to convert. 3 to some power is equal to 1 over 127. Or 1 over 27. So 3 to the x is equal to 1/27. So 27 is made up of 3 cubed. So 3 to the x is equal to 1 over 3 cubed. If I want that to come up to the numerator, that's going to be a 3 to the negative 3. And so now I have 3's as my base. Set my exponents equal. And I have x is equal to negative 3. See if you can do number 10 on your own.